Welcome to Maths with AJD. In this video, I'll be talking about frequency domain to time domain interpretation or spectral analysis. The previous video, I thought it would be the last, but then I got this request to clarify how to really interpret whatever results we get in the frequency domain in the time domain. Okay, so I've set out on this journey to really clarify that, talking about frequency domain. So whatever, when we carry out spectral analysis, we are translating data set or signal in the time domain into the frequency domain. So after doing the analysis and getting all the results, what will be the implications of those results in the frequency domain back in the time domain? That is the essence of this video. Okay, so our learning goals, by the end, of course, you'll be able to understand the theory behind frequency analysis of financial time series. Yeah, well, I used a time series that is financial in nature. Talking about like maybe stock price or something. So I have that right here. So this is it. I call it's a CSV file called financial prices, and it has just two columns. Um, we have just two columns for that. We have dates. Of course, it has to be time series. And then we have close, like maybe the closing price of a particular stock or a particular share, something like that. So, and we have 200, that's starting from January 1st, 2024, down to the end, which is, I think this should be 4th of October, 4th of October 2024. So that's 200 data points. So that's what we have right there. So that's the data set we are using in this situation. All right. So having taken care of that, so yeah, we could actually use any of the examples we have carried out, like maybe a biomedical one, maybe for all those things like ECG, EEG, and all that. We could actually do mechanical vibration and all that. But I think using financial time series, or we can even use temperature, right? But here I'm using a financial time series, like that. So then after getting that, we apply fast Fourier transform to returns, identify significant frequencies. So, that's part of that. Once we identify the significant frequencies, so there are many frequencies when we apply FFT, but not all of them are meaningful. But then here we are interested in identify the significant frequencies, and then we interpret their economic meaning, right? Then afterwards, we reconstruct time domain signals corresponding to cycles, be it weekly, monthly, quarterly, or annually, right? Then we then pinpoint when each frequency mattered most. We want to pinpoint when each frequency mattered the most. Okay, so let's go ahead and talk about the data preprocessing. So, like I said, we are using the financial underscore prices CSV data set. But of course, if you check it, it most likely is not available here yet. But in previous videos, I had shown how to upload a data set. So you just click on this file thing here, and then you point at this, you see it, upload to session storage. So I click on this now, then I go to locate that data set. So it's inside the spectral analysis folder. Then I have this here, financial underscore prices, and I just open that, and then it tells me ensure that your files are saved elsewhere. This runtime file will be deleted when this runtime is terminated. So once we are done here, well, you won't find this data set here any longer. So that's why you always want to make sure you have it saved somewhere where you can always access it in case you still need it later. All right, so talking about data preprocessing, first of all, we talk about financial time series like prices, maybe stock price, share price, whatever price you're thinking about. So they are typically non-stationary, right? So, and in the previous videos, we had talked about stationary and non-stationary series like that, and they have specific types of applications for them, right? Specific kind of treatment when it comes to spectral analysis. So, fast Fourier transform requires stationarity, but most financial time series are not stationary, right? So, but fast Fourier transform requires stationarity with constant mean and variance. In that case, we can then use log returns instead of raw prices. So we could have used raw prices if we had stationarity in the time series for in financial time series. But because we don't have that now, we can't use raw prices. We go ahead and take the log returns of the prices. And that means we have R of T, R sub T equals the natural log of P of T. That's the price. So that's the current price all over the price before now, something like that. So that's what this is about. So we take the log of the current price of our previous price. So we also need uniform time spacing. So we index the data to business days. Of course, if in financial terms, right, we're talking about business time, business days. You talk about the daily, weekly, and all of those kind of windows. So here, of course, we've uploaded the file, as you can see here already, financial underscore prices, and then we look at the code for that. So of course we need to import numpy as NP. We almost always need that. Then we are analyzing data. We need pandas for that. We need to visualize. We need pyplot. Then of course we need fast Fourier transform. They're talking about spectral analysis. So we need to bring that from numpy. And there are other ones that may have come from SciPy, but I don't think we need that right now. So how do we load the data set? We could have, well, there's a very easy way to load it. We could just come here straight, but I mean, here we have just chosen to go this other way. So we say part underscore two underscore CSV. So we load the financial underscore prices.csv. Then we convert that CSV document now into a pandas data frame. And that means we have PD, which is pandas dot read underscore CSV. Like I would usually say, read underscore CSV is a function inside the package, the library called pandas. So, and then we are reading the path to CSV and we pass the dates, right? So then we now sort values according to date. In case the data set was not sorted, so this is where we sort it. What I have is sorted, by the way, but if it wasn't sorted, we could actually sort it from here. Okay, and then we now have we now re-index the data set, the data frame. We bring it well, maybe to see what is happening at each step, I could just say print. So print PDF. So you see what it was like there. Print PDF, print DF, and then here, after set with re-indexing, you also see what happens. You also print the data frame here. Then after doing all of that now, so we set index based on date. We see all of that, and then after all that has been done, we can now set we say all underscore bd is equals pd dot bdate underscore range, and then we have the minimum, maximum, and we re-index for this. We can print this again also to see what is happening there. So we can see what is happening every step. Then finally, after we can now take the log underscore return. So to take we compute the log returns, right? So we have df. So it's like we are creating this new column in the data set, because so far we have just date and close, maybe the closing price or something like that. So say log return equals np.log df close.df. So that's like the current price over the previous one. And then line 22, we are dropping, by after taking log, it is possible we get some not available value. So we drop those and then we finally have df right here. Okay. So if I run all this now, we get, so the first case is this, like the raw data. So you can see this is the raw data right here. But Python starts counting from zero. So for 200 rows, we have 0 to 199 numbering. So 200 rows by 2 columns, we have all of this. So the next one we are printing is when we index using date, right? So if we index using date, we cancel the normal pandas index. So we are using date for indexing, as you can see here. So the other thing is gone. Then apart from that, then we finally, oh, okay, I'm supposed to say print df here. So print df. Yeah. So print df here, we are not doing numbering according to days. So where is that now? We have 200 rows by 1 column. Yeah. So we have this. So we index according to dates. So we re-index to business days, right? Business days. I don't think there's no much difference between these two, because the date is what it is already. And then after doing that, the next thing that is done is the log returns. So for log returns now, we can then have, so you see we have some log returns right here. So we have all this. So by the time we now do the log returns, and then we also remove not available values, what can I do? I want to see if I can print. So if you print this, maybe I should actually print let me also do another print here. Let me print DF here so that we can see all the 200 rows before one is dropped. So that means that most likely after we do the log return, there's a particular value there that is undefined. Yeah, you can see the first value is not available. So you can see we still have 2 rows and 2 columns. Or this line 24 is dropping that not available value. And that's why at the end of the day, we now have 199 rows by 2 columns. That's what exactly we have here. So that's us processing the data. So the insight you can see from that is that we now have a clean stationary log return series with uniform spacing ready for fast Fourier transform. So the data is ready. So far it has been in time domain. But by the time we go fast Fourier transform, we are doing the spectral analysis. So now the next thing is Fourier transform and power spectrum. So this discrete Fourier transform, DFT, decomposes the signal into a sum of sinusoids, like we know from the beginning, following this formula that x of f equals summation from t equals 0 to n minus 1, x of t e raised to minus I to pi ft. And then the power spectral density, PSD, measures the variance explained. The variance explained at each frequency. That is what the power spectral density measures. And that is PSD of f is the square of the absolute value of x of f all over the number of frequencies, I believe. So here, now we also need to understand that frequency, which is in cycles per day, or yeah, because we have a daily data, it actually corresponds to period. So T is 1 over F in days now. So if any frequency you have, if you take the inverse, you get the period. So it's more, this is a very basic formula to convert from frequency to time and from time to frequency, like that. So here we have, so we are trying to do the Fourier FFT and the PSD. So here we have, first of all, our signal now, which is X, is now take the data frame log underscore return. That's you're taking the log return column, which you are using because we already know the other time that because of the non-stationarity of financial series, we have to convert the closing price into log return, which we have done. So here now what we are doing is we are demeaning it. We are removing the mean to take care of some noise. So X is df of log return dot values minus df dot log return dot mean. So we are removing the average value of log return from the normal log return. And then N is the length of the signal itself. And then DT is 1.0. That is 1 business day, right? And then we are taking the frequencies like this. So this talks about the frequencies. So that the RFFT frec into N equals D DT. D equals DT, that's frequencies. And we have X now, which is RFFT of this X up here. That will give us the Fourier coefficients. And then the PSD itself is the absolute value of this X now, all right, all over N. That gives us the periodogram. All right, so if you run this, of course, we won't get any result, but then the visualization will be done here now. So here we are plotting the X label is frequency, the Y label is power, and we run this. So, and this gives us the periodogram of the returns, right? So this gives us periodogram of the log returns like that. So in this case, we have the power up here, and then we have the frequency here, talking about periodogram. So next, we move on. So what is the insight we get from here? The insight is that we have peaks. We have the peaks in the power spectral density. They show us dominant cycles in financial returns, be it weekly or monthly. But of course, it is still in the frequency domain. So that's why we keep moving until we get it back. So another thing we want to do next is we want to detect significant frequencies. So you can see there are all kinds of frequencies here, but there are some frequencies that are really significant. So we want to detect significant frequencies. So because not all peaks matter, many are just noise, right? Some peaks, some dominant frequencies may just be noise, right? So we want to detect the real important ones. So a simple heuristic, that is frequencies with power greater than mean plus 2 times standard deviation of power spectral density are considered significant. So this is the way you know which one is significant or not. I think I want to put that in bold. So we have a simple heuristic that if frequencies with power greater than the median plus 2 times standard deviation of power spectral density are considered significant, like that. So I think that helps. So each significant frequency corresponds to a periodic cycle. We can have daily, weekly, and things like that, as you're going to see. Then we have the mask, frequencies greater than 0. And then we have frequencies underscore NZ, that's frequencies of the mask. Then we have PSD underscore NZ, that's PSD of the mask. And then we have like a threshold now. We have that TH threshold. It's like we have NP dot median of power spectral density plus 2 times standard deviation of the power spectral density. And then we now have sig underscore IDX, that's NP dot where PSD NZ, this PSD now is greater or equal to the threshold. So that there we are getting the significant frequencies like that. And then next we order, so we can, that's more like some kind of sorting. So we have NP dot add sort PSD NZ into of this now, numbered from the back, right? So, and then we have the top index, we have significance, all of this. So you then have top frequencies, top periods. So top frequencies will be frequency underscore NZ into top index. And we have the top period, that's one of our top frequencies, right? So if you get frequency, you can take the inverse, you get period. If you get period, you take the inverse, you get frequency. So that's one easy switch between frequency and time domain. So that I think the ultimate secret of moving from time domain to frequency domain lies in the fact that period is 1 over frequency and frequency is 1 over period. Then we also have the top powers, PSDNZ, top IDX, we have that. And then we have PIX DF, that is PD dot data frame. So we're doing this data frame now. We have frequency in cycles per day, so it gives us the top frequencies. And then we have the period in this, it gives us the top periods. And for the power, we have the top powers, and we run this, and this is the kind of thing we get. So this has helped us to identify the top frequencies like that. So yeah, 5 of them, so we have frequency in cycles per day, 0.20. The period is 4.97, and the power is 0.00612. This one has been ordered from the highest power to the lowest. And then for the second one, we have 0.165829. The period is this. So we have all of these things going on like that. So that way we have identified the significant frequencies. Now, going forward, we see that the insight attached to this is that an example interpretation will be that 0.2 cycles per day is the same thing as 5 days for weekly. So 0.048 cycles per day will be the same thing as 21 days for monthly. So in short, whatever cycles per day we have, divided by, just take the inverse, like, 0.02 is like 1 over, so this is frequency now. So in period, that will be 1 over 0.2. That's the same thing as 10 over 2, which is 5. So that gives us 5. So we can actually take the durations of all this by taking the inverse, and then it will tell us the kind of what it translates to in day and all of that. Okay, so then let's go ahead and talk about the band definitions. So we can group frequencies into bands to capture meaningful cycles. So weekly is approximately 5 days. Monthly, of course, we have 5 working days. Monthly is approximately 21 days. That's like 21 working days. Quarterly is like 63 days. That's 21 times 3. Because a quarter is 3 months. But of course, we are talking about working days in the 3 months. Then annual will be 252. That's like 20. Is it like annual is quarterly times 4? Yeah. So 63 times 4. And then we have high frequency, which is less than or equal to 3 days. Okay. So in this case, now we do all this whole grouping. We have 1 over 7, 1 over 3.5. That's like half of the week. Then for monthly, we have this whole thing going on like this. Okay. Then we can then have the time domain reconstruction. Okay. So we can reconstruct time signals for each frequency band by keeping only the Fourier coefficients in that band, zeroing out all other frequencies, then applying the inverse FFT, that's the inverse fast Fourier transform. Mathematically, X band of T is like F inverse of X of F dot 1 of F, where F belongs to the band. So where this is an indicator function that is if F lies in the chosen frequency band and 0 otherwise. So in this case now, so we have all the components. So for name and F low Fi in bands.items, we have the mask band frequency greater than low and frequency less than or equal to high. Then we have the X band, NP0 like X band mask, blah, blah. And we have all of this. And so this gives us the necessary information. So for each day now, we have what we are doing here, we are doing the time domain reconstruction. So all the results we have got, we are taking it back into the time domain, and that is why all those values we got the other time. This is the weekly. These are the weekly cycles, monthly cycles, quarterly cycles, annual cycles, and high frequency cycles like that. And another thing we are doing is we can then do the band contribution. How does each one contribute to the overall thing. So we have band contribution for the weekly. This is for the monthly. This is for the quarterly, and this is for the annual. And then if we have high frequency, this is what this looks like. Now, the insights we draw from this is that we can see daily contributions from each cycle band. So from each cycle band, we can see the daily contributions based on the cycle band we choose like that. Because for each cycle band now, for each day, we have an approximate contribution for any of the cycles we choose to go for. Okay, so then we can then talk about the top dates of contribution. So if you want to know which days actually contribute the most to the stock price or share price or whatever we are bothered about, so we look at the top dates of contribution. So the absolute amplitude of a band indicates how strong it's contributed. Sorting gives us calendar dates of peak cycle effects. Okay, so and the code that goes with this is we have, of course, this is an initialization. We say we open an empty list for the rows so that we can then append values to them later. That is what we see in line 6. So we now say for name in comp underscore df dot columns. That's the comp underscore df dot column is what we had up here where we did the time domain reconstruction. So and then we get so for the top date contribution now, so for naming that in all those columns, we say s underscore abs, that's like absolute value. We have com.df name.absolute I log 10 to minus 10. So we are trying to avoid the edges with this. Then we have the top dates equals s underscore abs dot n largest 5. So we are picking the largest 5. So if you want the largest 10 or something, you can pick. But I don't think there's no point picking the largest 10 because at the end of the day, we just want to see the top contribution for daily, weekly, and all the rest. So then we now say for DV in top dates, top underscore dates dot items, then we now append to the to rows now. Rows is the empty list. So append the band name, the date, in this format, year, month, and day, and then we have the absolute contribution. That's the absolute value of the contribution, which is actually our V here. So in this case now, if you just run this is what we get. So for weekly, approximately 5 days now, we have this whole thing. So you see that the peak is seen around 26th of April 2024, according to the data set you're working with. And then the absolute contribution is the highest here. So, and then for monthly, the absolute contribution is always the first. You can see it's decreasing because it's been sorted. For monthly, we have 21st of January 2024. That's the highest monthly whatever we had, for the absolute contribution like that. For quarterly, the first one is 29th of March 2024. And then for annual, it's 28th of February 2024, like that. And we have high frequencies. It's like 12th of April 2024, like that. So the insight we see from here is that the absolute amplitude of a band indicates how strongly it contributed. So of course, the band is talking about the frequency that we have now taken back into the time domain. So sorting now gives us calendar dates of peak cycle effect, right? So example interpretation, for the weekly, we saw all the dates now. The first one is like 26th of April, April 2024. So for each one, we have just extracted this one. So weekly cycle picked on 26th of April 2024. Monthly cycle picked on 22nd of April 2024. Quarterly cycle picked on 29th of 29th of March 2024. Then annual cycle picked on 28th of April of February rather 2024. Then we have high frequency cycle picked on 12th of April 2024, like that. Okay. So maybe one thing I should have done from the beginning was probably to see the raw data, right? I forgot to do that. Okay. So maybe let me see what I can do in that regard. So after seeing all this, before even doing this whole thing now, so let me try to create something that shows us the raw data. I think normally that's the first thing that should have been done. Okay. So I can use AI for that. I'll just say plot the raw data. Plot the raw data before we even started transforming. Plot the raw data. Okay. So I can then move that one before processing. Yeah, so we just want to see the raw financial prices. So we are doing close and all that. So if I run this now, yeah, so this shows the this is the raw price we have. So these are the price against date. So this close now against the date. So I think I should move it to the top of before we started pre-processing. Okay. Yeah, I think it's fine here. Before we started pre-processing. So data processing, right? So here I can just say raw data, raw data, and or let me say raw data plots. Okay. So this is what the raw data looks like from what we have there. So you can see some, some kind of seasonality or whatever we can say in all of that. And then coming here now, we have the pre-processing. So this is where the pre-processing takes place, like that. So we have the raw data plotted here like that. I think I'm trying to see. I guess this should come mm, because if I rerun this now, it may not work perfectly. So maybe what we should have done first is to, okay, I guess I should bring this whole thing. Yeah, I think it's better to bring this whole thing here. Okay, let me see what I did there. Yeah, that's fine. So we should bring this whole thing on this on the top of this so that that's the only way it can make sense because if I want to rerun it, it needs all these things to work. So yeah, so I think we're good now. Or let me even try from the beginning. So I can restart the session. Yes. Okay. So I run this. We have the we have the data frame and then we have the plot right here. Then the preprocessing can then follow. Okay. So the preprocessing goes all the way to the log returns. And then we can talk about the Fourier transform, which I had done before this goes. And then we have this. Then detecting significant frequencies, which we had done also. We have this. And then we're trying to define this. So then for here now, so we group frequencies into bands to capture meaningful cycles. So weekly, okay, I think we had done this too. We had done this also. And we did time with domain reconstruction using that formula. So we have this. Then of course we were here. So and we saw the contribution of each cycle into the whole thing. So now we can see daily contributions. Then we also did the top contributions, top dates contributions. We have them, and then we identified the peaks for each cycle, how where the peaks. Then now we are going to the rolling variance share, right? For the rolling variance share, we measure how much variance each band explains within a rolling window of length W. So we have share underscore band of T equals variance of X band window, variance of X window. So this ratio tells us at each time, T, what fraction of the total variance is explained by the chosen frequency band. It highlights when specific cycles dominated the dynamics of the time series, right? So talking about rolling variance share. So in this case now, we have wing 63. So X squared is X minus X mean squared, and then total energy. So it's more like doing some kind of deviation thing because we're talking about variance, right? So we have total energy is PD series, X2 index, all this. Then I think this 63 now, it has something to do with is it yearly or week quarterly? I think it must be quarterly. 63 is approximately quarterly from what we've seen before. Yeah, I think it's like that. So we are looking at a quarterly window because in financial reporting, there's a lot of, some reports are done on a quarterly basis, first quarter, second quarter, and things like that. So if you look at that, we have, of course, because we are dealing with a quarter, so we have so many not available value because of the computation that would have been done in the process. Because since we're talking about like moving, it's a rolling share, that's maybe bears some kind of resemblance with moving average, where some data become non-available because we have rolled them to the first. If you are doing like 3-day moving average, for instance, we don't have figure in the first 2 places or so. We only get the first result in the third place. Okay, so here now, for name in roll underscore df dot columns, we now want to have the rolling variance share, the name of whatever name that is. So, and we have this plot. So rolling variance share weekly, approximately 5 days. Then we have rolling variance share monthly, approximately 21 days. Rolling variance share quarterly, 63 days roughly. Rolling variance share annual, 252 days roughly. And then if you have rolling variance share for high frequency, that's less than or equal to 3 days. This is what it looks like. Okay. And then the insight here. So what insight can we draw from here? We can get the insight from this code. So for name in roll underscore df, we get the band share, the maximum share, the peak date, and all that. So this gives us the insight from that. And we can see that for the weekly cycle, the weekly cycle explained peak of 45.6% of variance around 24th of May 2024. The monthly explained peak of 12.1% of variance around 28th of March 2024. And for quarterly, it explained peak. We are talking here about how much the variance is explained, what fraction of the total variance is explained, right? So by the chosen frequency band, right? So using a chosen frequency band, right? So for the annual cycle explained peak of 1.3% of variance around 3rd of September 2024. And for high frequency explained peak of 46.3% of variance around 5th of September 2024. So that's what that does for us. And then we can also have the band only price parts. So if you cumulate the band-only returns, you obtain a band-only price index, which is P underscore band of T equals P naught exponential summation from tau equals 0 to T, X underscore band of T, where P of 0 is the initial price, e.g. 100, X band of tau is the reconstructed return from the chosen frequency band. This shows how much each cycle alone would contribute to the growth or decline of the price index. So band-only price path shows how much each cycle alone would contribute to the growth or decline of the index. So, and this is how the coding goes. Price of 0, we say 100. Band price, we make it maybe an open set or something. So for name in comp underscore df dot columns, that we had done this before. So the cum is now np.cum comp sum into comp df of name. Then we have the band price. So 0 times whatever we get from here. Then we have band price df. We have that data frame for band price, and then band price df dot plot. We plot band only price indices, and then we show that plot. So, and this is what this gives us, band only price indices. So we have so for the weekly, that's the blue one. It's the frequency is a bit higher. For monthly, we have the orange one, and then for quarterly, we have the green, and for annual, we have this one. It's just the frequencies reduce as we increase the window. And then high frequency, of course, that one has the highest frequency, as you can see. Okay, so the insight we draw from here is that this helps show how much each cycle alone would move the market, right? So it shows how much each cycle moves the market. So with all this now, we see that in conclusion, fast Fourier transform reveals cycles in financial returns. Inverse fast Fourier transform maps them back to time, letting us see when cycles mattered most. Then weekly cycles often reflect microstructure. Monthly cycles will show us fund flows and payrolls, while quarterly cycles will show us earnings and rebalancing, and annual cycles will show us seasonality. As you can see, the annual cycle shows how things go low around April, May, June, like that. And then they are at the top around January, February, and they go towards the top again around August, September, October, like that. So we see that the annual cycle shows seasonality. So this is my my modest attempt at trying to interpret whatever we have done using spectral analysis in the frequency domain back to the time domain. I hope this helps. Thank you so much for listening. With this, I come to the end of the video. Of course, if anything comes up again, I might have to do other videos, but this is but for now, this is where this stops. Let me know how helpful this is for you. And of course, if there's something else you'd like me to try, feel very free to let me know. If you have subscribed already, thank you so much. If you haven't subscribed, of course, you know you've been missing a lot. So go ahead and subscribe, hit the notification bell so you can always get alerted each time a new video is released, right? And of course, you can take it a step further. You can become a member of the channel by clicking on join, and that comes with some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths, Python, data, and all of those things. Right. Bye.